This is another episode of Basic Mechanics, and this time we are tackling analysis of structures. Very interesting topic. We need to understand how to analyze what? Structures. It's very necessary. So let's look at how and what structures are we going to analyze here. Two types of engineering structures that we are going to what? Consider. Two types, and they are namely as for trusses and frames. And I guarantee you this analysis of structures is very interesting, and if you know how to go by it, it will help you in your engineering what? Activities, trusses and frames. And let's look at it. Trusses and frames are made up of several interconnected what? Bodies, referred to as members. In our daily activities and on our engineering field, we need what? Trusses and what? Frames to support most of our materials, or we need them for most of our activities, both trusses and what? Frames. And here it is telling us that a truss and a frame are made up of several interconnected what? Bodies, meaning several parts come together to form what? A truss and a frame. And each part or each body is called what? A member. So together they form what? The members of what? The truss. Are we good? So if we have 13 interconnected bodies, each one is called what? A member. And we have 13 members to form the truss and the frame. Are we good? So now we are saying we are making analysis of engineering structures such as trusses and frames. How do we then differentiate between a truss and a frame? It's very simple. Let's look at the difference. A truss is composed of solely slender members connected together by what? Pin joints, and it is also designed to support load applied at the joints only. Take the definition very well. A truss is composed of what? Solely slender members, meaning its members are what? Slender. That's their lightweight, their size is what? Smaller. They are not heavy members. And so if you want to identify a truss, first check the members. They are slender. Are we good? And look at how they are connected. They are connected together by what? Pin joints. Do we remember during equilibrium we saw pin what? Pin joint. And for each pin joint we know what to do. We know the reaction at what? A pin. We know an upward and what? A horizontal what? Reaction. Rx and R what? Y. So for a truss, the members are what? Pin joints. So you know how to represent your reaction. And they are designed to support loads applied at the joint only. At the joint. So for a truss, sometimes there can be a question on what? One of them, and you may not know which type of structure they are talking about, either a truss or a frame. Although the solving will help you, if you understand, you solve it. But to identify it as a truss, first check if the load, the forces are applied at the joint. Are we good? So if the forces are applied at the joint only, then it's what? A truss. And the members will also be what? Slender, connect. So we can consider three things. Slender what? I want you to understand this analysis of structure because it's a broad what topic. We need to take it one by one and understand so that when we get to problem solving, it will be easy. They are slender for truss. Two, they are what? Pin jointed. And three, load at what? Joint. These three things will help you identify what? A truss. What about a frame? Then a frame, on the other hand, may be designed to support both moments and forces applied at any point. Check this, any point in the structure. So you see the difference. A frame is designed to support both forces. Remember, this truss is designed to support what? Loads, which are what? Forces, no moments. But a frame, on the other hand, may be designed to support both moments and forces. And this time, the moment and the force may be applied at any point on the structure. So for frames, you can apply at the ends, at the middle, and at any point. So that's the clear-cut difference between a frame and a truss. So when we are solving question, we will first analyze if this structure is a frame or this structure is a truss, and it will help us to what? Get whatever we are looking at. Are we good? So by now we know the difference between the structures, that's a truss and a frame. So let's continue. Now we have what? Our diagram. We have, this is a truss and this is what? A frame. Let's check if what we learned was true. First, we saw that with truss we have slender members, and two, they are what? Pin jointed, and three, loads at what? Joint. So let's check if they are slender, meaning their sizes are not what? Bigger. Yes, this truss, look at the size of the members. They are very slender. Yes, so this first one is what? Obeyed. Pin jointed. Each member or two or more members are what? Pin jointed. Let's look at this joint. It's pin. Yes, this joint is pinned. All these are pin what? Joint. This is pin, and this point is also what? Pinned. So a truss is pin jointed, is obeyed. Load at what? Joints. Let's look at it. We have F1, which is load 1, and F2. F1 is applied at what? A joint. And F2 is also applied at what? A joint. Are we good? So for this truss, we cannot apply any force here as F3. It is what? Wrong, because a truss supports loads at joints. Are we good? So it is also obeyed. What about a frame? We saw that a frame supports both moment and what? And forces. And two, members are not slender. They are not slender. Slender knots. And also loads applied anywhere. Applied anywhere. Okay, so let's check. Moment and what? Force. Yes, there's a force 1 here. There's a force 2 here. So it supports forces. Are we good? Slender knots. Their sizes are not as compared to trusses. They are bigger in size as compared to trusses. Let's look at the members. This is member 1, this is member 2, this is member 3. Remember, this truss has 1 member, 2, 3, 4, and 5. So 5 members here. Are we good? And this frame has what? 3 members. And looking at the members, they are not slender. Compare size of member 1 in the frame to the one in the truss. You see the clear difference. These ones are what? Bigger in size. So easily you can identify what? A frame. And loads are applied anywhere. Let's look at the joints. These are joints. 1, this is joint 2, and this is joint 3. Even the loads were not applied at the joints. So look at F2 and F1. They are applied anywhere on the member. And this makes it what? A frame. So I can apply another F3 here. F3 as what? My force. They are not what? On the joint. And this will what? Be a frame. Are we good? Alright, so analysis of trusses and frame is based on the principle. How do we then analyze and solve for forces on a frame or on a truss? And what we are going to do here is that we are only going to make analysis based on the principle that if a structure is in equilibrium, if this whole truss or this whole frame is in equilibrium, and yes, every time they are in equilibrium, then each of its members is also in equilibrium. Are we good? If this truss, the entire truss and the entire frame is in equilibrium as it is standing, then each of its members, so member 1 to 5, each member is also in equilibrium. Because if this member is not in equilibrium, the whole system won't be in equilibrium. So we assume that since the structure is in equilibrium, then each member I take will also be in equilibrium. Then if they are in equilibrium, what do we do to analyze the forces in each member? One, by applying the equations of equilibrium. This is the reason why we first tackled what? Equilibrium. We solved how to analyze the reactions. So we are going to apply the equations of equilibrium to the various parts of a frame or truss. All the forces acting at the joint can be what? Determined. Are we good? So remember, the main focus of trusses and frames is that we want to make analysis of the forces acting in each member. What's happening after we load our truss? What is happening to this member? What is happening here? What is the force? Is it tensional or compression? What is the magnitude? Are we good? So we will calculate for those things. And what we are saying is that we take the entire system to be in equilibrium so that when I remove just a member, I'll make analysis at a joint and I'll apply all the equations of what? Equilibrium. And we know that the equations of equilibrium, summation of what? Fx is 0, summation of what? Fy is 0, summation of a moment about any point is what? Also what? 0. Here we go. So we apply these equations at any joint to make analysis. Don't worry. You will solve, and as the lessons go, you understand how to make this deduction, how to apply this equation. But for the meantime, let's pay attention to the difference of what? The structures and how we are going to what? Analyze them. It's very simple for analyzing what structures and solving questions. Simple trusses. So we are starting with truss. The trusses. Okay, so the simple, we assume it to be what? A simple truss. Are we good? First, there should be some assumptions. Engineers mostly do some assumptions to what? Make calculations, and it helps a lot. So as we are going to tackle simple trusses, what are some of the assumptions we should make? So these are trusses. I hope you've seen them around. Yes, sometimes the network poles, they are our network poles. They are all what? Trusses. Those are clear examples of trusses. You can see members. Each joint, they are jointed. Are we good? All right. So let's look at an analysis where if we are if we are going to solve each truss to determine the force in each member. So our main focus of analyzing structures is that we want to know what is happening to this member, what is happening here, what is happening here, the force in each. Are we good? All right. So what are the assumptions? First, to analyze trusses, it is assumed that the members are connected together by pin joints only. Are we good? So we analyze trusses in a way that we assume that the joints are only pin jointed, no roller at the joint. At the joint, check, every joint is pin what? A pin joint. That's the first assumption. Okay, established. In an actual truss, but in an actual truss, the members may be fastened together by what? Welding, riveting, or bolting to a common plate known as a guest plate as shown in the figure. So in reality, it is not always pin joint. Sometimes it can be a rivet, it can be a bolt, it can be welded to fix the joint. But for analysis sake, for calculation sake, we assume that any truss we see is pin jointed. But in reality, there are other ways of making a joint established. And the third point here is that it is also assumed that the members of the truss are all straight and that all the loads are applied at the joints only. This assumptions are very clear. Each member of a truss is assumed to be straight, like each member. A member of a truss is from one joint to another. That's what we call a member. So from this joint here, this is one member. From this joint to another joint, this is a second member. To another joint, this is a third. So this 10 is not a straight, it's not a whole member from the first joint to the upper joint. No. From one joint to another is a member. It can be removed and replaced. Are we good? All right. So we assume that each member is straight so that it can help us make what? Analysis. And that all the loads are applied at the joint. Remember, the qualities of what, or the properties of a truss, the loads are applied at the joint what? Only. Are we good? So once we know these assumptions, our deductions on simple trusses will be what? Very easy. I hope we are taking the lessons very seriously and we understand it clearly. So these are trusses. This form and that form. You can see their names in this form and this separate. Are we good? Alright, this is like more or less like a triangular form, and this is like something like a trapezium form, but they are all trusses, and analysis is the same. Once you know how to apply your equilibrium equations, you can solve them. But don't worry, we will solve and you understand it clearly once we stick to the assumptions. Okay, so what again should we do? Each member has forces acting at its ends. When we take a truss, each member, remember I told you from one joint to another, is a member. So this, how many members? Let's count. 1, from here to here, 2, this 3, this 4, 5, this is 6, this, the straight one is 7, this is 8, this is 9, this is 10, 11, the straight one 12, this is 13, and this is 14, this is 15, this is 16, this is 17, 18, this is 19, this is 20, and this is 21. So in this class, we have 21 members. Interesting. 21 members. And what we are saying about trust is that each member has forces acting at its ends. So for example, I remove this is, let's take this as this joint as from A to B. You can label it. This is from A to B. So let's take A to B. This is the member. And what we are trying to say is that as I took AB, this is A to B, the member A to B from the truss, it has forces at its ends because it is going to support what? A load. And you know, once it is going to support a load, there is going to be a force induced in the member. And these forces are what? At its ends. Don't forget, so that when we are making analysis, we know how to place our what? Forces. They are placed at its ends. Are we good? Okay. When these two forces tend to elongate the member is said to be in tension and it is called a tie objective. So anytime I make analysis of a member and I see that the forces are what? Elongating the member, then the member is said to be in what? Tension. And that state of the member is called a tie. Are we good? So objectives, forces that tend to elongate members of a truss, that member is said to be what? Is a tie. Are we good? So we will see. Don't worry. We'll see how to replace these forces, how to place them and see that, oh, this force is in tension, this one is in compression. We'll solve questions and we'll get to know. But these are the theory behind. You must understand it clearly. Once the forces are placed at its ends and you analyze that it is elongating the member, then the member is said to be a tie. That's in tension. And when the force tends to compress the member is said to be in what? Compression. And it is called a strut. Are we good? Looking at this, after the analysis, I saw that AB was being what compressed. You see, you just don't put the forces anyhow. From analysis, you see that these forces are what compressive, and we call that structure as what a strut, or that member as a strut. Are we good? Very often in the force analysis of trusses, the weight of the members are neglected. Are we good? When we are analyzing structures, take this very seriously. When we are analyzing structures, someone will ask this question: the weight of the members are neglected. Weight what? It's very necessary. Neglected. Are we good? We neglect what? The weight. Why do we neglect the weight? For example, we will see how to find the forces in each member. Don't worry about that. But when we get there, as we are making analysis in each member, what we are trying to say here is that the weight is not what added, because now the load this structure is going to carry is heavier than um the weight. And remember, we also said the members are slender, they are light weighted, so the weight can be negligible. Very good. These are the two reasons. The reason why we neglect the weight is that one, they are slender, meaning what? Less weight. Very good. And if they are less weight, then two, the weight is what? Small as compared to the load. Small as compared to the load, compared to what? The load being carried by the entire structure or the member. So we neglect the weight, and where the weight is not negligible, a satisfactory analysis can be normally be obtained. So in a question where they say you should not neglect the weight, mostly in frames, the weight is not what neglected, because you see they are not slender. They have a reasonable what weight. So a situation where the weight is not neglected, we find a way of what replacing it on the member. And this is how we do it. We place the weight, we divide it into two and place half at each end of the member, this like this. So maybe if this is a 50 Newton weight member, we place 25 Newton here and place 25 Newton on the other side to make analysis. Don't worry, we will solve all this and it will be very simple for you. These are the theories behind trusses. The theory behind trusses, and once you take this seriously, you get to understand that trusses is not what difficult. It's just a matter of what knowing the rules, understanding how to go by it, and with that, you are good to go. So just follow the episode for the analysis. So in this, we just tackle the theory, and as we move forward, we are going to look more deeper into analysis of structures, and you will love it. Thank you for watching this episode. Look out for the next episode to get the entire lesson. Thank you.